Hello, good afternoon all, and welcome to this presentation. Before I start my presentation, I would like to express my gratitude for giving me this opportunity. And now, I will start my presentation by introducing myself. I am Addisu Tashala Fata, or you can call me Addisu or Addis. I'm originally from Ethiopia. I'm 38 years old. I earned my bachelor degree in electrical electronics technology in 2007 and I've obtained my master's degree in electrical power engineering in 2012 from Adama Science and Technology University, Ethiopia. Adama Science and Technology University is one of the two science and technology universities in Ethiopia which is funded by the Ethiopian government. Coming to my professional experience, in terms of my professional experience, I've been worked as a graduate assistant, lecturer, and senior lecturer at the same institute, Adama Science and Technology University, in the Department of Electrical Power and Control Engineering. Currently, I'm pursuing my PhD at the same institute. Today, I will talk about my academic and technical expertise. First of all, I will discuss about my research expertise, followed by my teaching experience, and finally, I will talk about my technical skills. Now, let's start by discussing about my research experiences. So far, I've been involved in about 5 scientific researches. In today's presentation, I'll present 3 of these researches where I've been served as a primary author. These are analysis of common mode electromagnetic interference in permanent magnet synchronous machine with fractional slot concentrated winding. Second, analysis of common mode current in 3-phase 4-wire permanent magnet synchronous motor with an improved neutral filter topology. And thirdly, an improved overview of shaft voltage and bearing current mitigation methods applied at the victim machine. Now let us see this research one by one. To be mentioned, all these researches are conducted after the beginning of my PhD. The first research is on analysis of common mode electromagnetic interference in permanent magnet synchronous machine with fractional slot concentrated winding. The author of this research are me, Mr. Zhao is my colleague, Dr. Getachew Birru is my Ethiopian professor, and Professor Roberto Leidhold is my German professor. It is already completed and published on IEEE conference. It is well known that conducted common mode electromagnetic interference is one of the major problems of the modern adjustable speed drive. The presence of common mode electromagnetic interference in electric drives can degrade the performance of the electric drive system, even leading to the premature damage of the machine. The primary causes of common mode electromagnetic interference in electric drives are the fast changing of voltage over time, most commonly called the high dV by dt characteristics of the converter, and the presence of parasitic capacitance in the drive system. As you can see from this analytical formula, the common mode current directly proportional or directly depends on the amount of existing parasitic capacitance. the rate of change of voltage per time, and the amount of common mode voltage and the amount of common mode impedance. The objective of this study is to explore the impact of winding configurations on machine vulnerability to conducted common mode electromagnetic interference. In this study, two winding configurations have been considered. These are the distributed winding and the fractional slot concentrate winding. As you can see here, this is a 3D view of model of the distributed winding, and this is a 3D view of a machine wound with a concentrate winding. And this is also the winding design of a machine wound in distributed winding, and this is a machine wound in concentric winding. Compared to the distributed winding, the fractional slot concentric winding machines have a reduced machine length, fewer number of slots, and a wider spacing between the slots. As far as parasitic capacitance is concerned, many researchers depicted that there are about 5 parasitic capacitances present in electrical machine. These are the parasitic capacitance between the winding and the stator of the machine, the parasitic capacitance between the winding and the rotor, the parasitic capacitance between the stator and rotor, and the parasitic capacitance between the bearing drive end and the bearing parasitic capacitance in the non-drive end. The magnitude of these parasitic capacitances depends on the number of slots, the height of the coil, stator's stack length, and the width of the stator teeth. As we can see from this analytical formula, the parasitic capacitances are directly proportional with the number of slots, and it is again directly proportional with the height of the coil and the stator stack length and the width of the stator teeth. Due to the reduced machine length, fewer number of slots, and wider spacing between the slots, fractional slot concentrate winding is expected to exhibit lower parasitic capacitances compared with the distributed winding. Since we do not have two the same sized motors wound in distributed winding and fractional slot concentric winding in our laboratory, the following methodology has been used to compare the two windings. First, a 2D model and finite element analysis simulation of an available 5.5 kilowatt induction motor wound in distributed winding is carried out on console multiphysics software. Then the simulated common mode impedance of the motor is compared with the actual measured common mode impedance of the motor. As we can see, this is a 5.5 kilowatt induction motor, and this is a model of that 5.5 kilowatt induction motor in console multiphysics. And we have compared the console multiphysics simulation result and the actual measured common mode impedance of the motor, and then we found a very good match of common mode impedance between the measured and the simulated result has been achieved. As we can see here, the common mode impedance, the simulated one and the measured one, is more or less good match with each other. Secondly, the same finite element method approach has been applied to another 60 kilowatt permanent magnet synchronous machine. The machine winding has been modeled and simulated both in fractional slot concentric winding and distributed winding. In this case, what we did is, this is a permanent magnet synchronous motor, 60 kilowatt permanent magnet synchronous motor designed for electric drives. So we modeled the winding of this machine, or we model this machine in COMSOL multiphysics. The actual it is actually wound in concentric winding. Therefore, we took the actual model and then we designed this machine for distributed winding, and we have simulated both. That means when this machine is modeled in distributed winding and in fractional slot concentric winding, we can see the result that from the simulation result, a reduced parasitic capacitance and an increased common mode impedance has been obtained by employing the fractional slot concentric winding compared with the distributed winding. As you can see, the parasitic capacitance in fractional slot concentric winding is less than that of the distributed winding. As well, the common mode impedance of the fractional slot concentric winding is higher than that of the distributed winding for the frequency level of our interest. In conclusion, the finite element analysis simulation in the result indicated that a promisingly decent decrease of parasitic capacitance and an increase of common mode impedance by employing fractional slot concentric winding compared with the distributed winding. Due to the lower parasitic capacitance and higher common mode impedance, fractional slot concentric winding is less vulnerable to the common mode electromagnetic interference. From the analytical equation of the common mode current, so if the parasitic capacitance is decreased, or if the common mode impedance of the motor increased, so reasonably the common mode current will be decreasing, because as parasitic capacitance decrease, the common mode also decrease, and as the common mode impedance increase, the common mode current also increase. Therefore, on top of the other advantages of fractional slot concentric winding for permanent magnetic synchronous motor, such as higher power density, higher efficiency, short intern, and high slot field factor, now less parasitic capacitance and less risk of common mode current is an additional advantage of the fractional slot concentric winding over the distributed winding. With this, these are what is presented in the paper. Now let's come to the second research, which is on analysis of common mode current in 3-phase 4-wire permanent magnetic synchronous motor with an improved neutral filter topology. Now this research is not completed. Actually, we have already obtained both the theoretical simulation result as well the practical result. So we are left with, now we are in the writing up of the paper to send to the journal. So I will present some of the points we have addressed in this research. According to the research in this research, the use of 4-wire electric drive system leads to a substantial reduction in conducted common mode electromagnetic interference when compared to a well-filtered conventional 3-phase 3-wire topology. This is due to the 4th wire provides us a safe common mode current discharge route. Therefore, as a result, in 4-wire topology, the common mode current always reduced when compared with the well-filtered conventional 3-phase 3-wire topology. Again, as described in the second research in this paper, the addition of neutral filter in the neutral wire results an additional reduction in common mode current. Also, the mentioned study effectively reduces the common mode current over a wide frequency range. Its effectiveness is constrained in low frequency spectrum, and moreover, the inclusion of the resistor in the filter also introduces an additional loss in the drive system. Therefore, the aim of this paper is to design an improved optimal neutral filter topology for the 4-wire drive system that can further improve the common mode current reduction performance without altering the drive performance and efficiency. The design of the neutral filter involves a series of steps. First, prior to the filter design, a high-frequency behavioral model of a 2.2 kilowatt permanent magnet synchronous motor were developed based on this paper, this research. And this is a per phase equivalent circuit model of permanent magnet synchronous motor, which is described in this paper. So by following the procedure mentioned in this paper, we are able to develop the equivalent circuit, the high frequency equivalent circuit of the drive system. The parameters of the equivalent circuit have been obtained from the common mode and differential mode impedance characteristic of the motor. So the advantage of this technique is that it doesn't require any detailed knowledge of the motor geometry, the material, and the winding configurations. So this is a experimental setup to measure the common mode and differential mode characteristics of the motor. As you can see, this is a 2.2 kilowatt permanent magnet servo motor, which is under load, under test, the motor under test. And this is a load motor, which is connected with this. And this is a impedance analyzer, which is used to measure the common mode and differential mode impedance of this motor at higher frequency up to 30 megahertz. The validity of the developed equivalent circuit is confirmed through a comparison of simulated common mode and differential mode impedance of the motor with practically measured impedances. So as you can see, once we develop the equivalent circuit of the motor, we have compared the equivalent circuit of the motor with the actual measured common mode impedance of the motor. So reasonably very good match between the developed equivalent circuit and the actual measured common mode and differential mode impedance of the motor. So it is simulated up to some 10 megahertz. Thirdly, we have proposed a neutral filter topology comprising a parallel LC circuit further connected in series with another capacitor. So this is a transfer function of this filter, and this transfer function is further approximated to this and this for lower frequency as well for higher frequency. In this study, 3 design criteria were considered to design the neutral filter topology. These are the neutral current criterion, efficiency criteria, and resonance overshoot criterion. The aim of the neutral current criteria is to limit the neutral current to an acceptable level. In this study, the level neutral current is limited to 1% of the rated line current. Now what we did is we measured the rated current of the machine, and then we took 1% of that rated current, and then we limit the neutral current to that level. So in order to limit the neutral current to an acceptable level, the value of the neutral impedance should be larger than the impedance of the optimal neutral filter capacitance. This neutral filter capacitance means the neutral capacitance value that results the possible minimum common mode current. That means This is obtained through the parameter switch simulation. We connect a variable capacitance to the neutral wire. Then we vary this resistance, this capacitance value from minimum to the maximum, and then we measure the common mode current at each level and as well the neutral current at each level. So by limiting that neutral current, not the neutral current go beyond the prescribed current value, and then within this range the maximum the minimum possible common mode current can be achieved. The capacitance value obtained at that point is called the neutral optimum value. Therefore, as mentioned, to limit this neutral current, always this neutral impedance should be the filter of the impedance of our filter should be less than or equal to greater than or equal to the impedance of this optimum capacitance impedance, and the same is true for high frequency also. The second one is the efficiency criterion. To improve the filtering capacity of the filter, the filtration should start at lower frequency range. Therefore, to shift the resonant frequency to the lower frequency range, F start or the new resonant frequency should be less than the actual resonant frequency. So we know the actual resonance frequency, the resonance frequency we want to our filter to work. So we have to choose a frequency less than the resonant frequency, and then once we choose this resonant frequency, we will equate that resonant frequency equals 1 over 2 pi LC. Therefore, we can get this equation. Bear in mind that the capacitance value should be approximately equals with the Cn opt that obtained through parameter sweep. So from these four equations, 1, 2, and here we have two equations. So we know that this value is already known, and we know this frequency range is known. Therefore, from these four equations we can derive the Cn1, Cn2, and Cln value, and then the value of the filter parameter can be determined by solving the above equation simultaneously. As a result, the value are adjusted as follows. The inductance is actually this is not the exact result because we can, since we we have to approximate to the next standard value. We have to make take approximation. So the Cn1 is approximated to this, and Cn2 is finally approximated to this one. And further, the developed filter should be again evaluated for resonance overshoot criteria. That means the resonance overshoot criteria aims to restrict the drive system's step response overshoot to a maximum of 5%. That means the step response of the drive should be less than or equal to 5% of the overshoot. The overshoot should not exceed 5%. So if the overshoot is greater than 5%, we have to put a damping resistance that will be inserted in parallel with Cn2. So we have to connect a damping resistor in between, in parallel with Cn2 if the overshoot is greater than that of 5%. However, in our case, since the percentage of overshoot is within the limit, there is no need to put damping resistor here. So for the purpose of comparison, another neutral filter topology is also designed based on the filter topology presented in 2. So we have also designed another filter, and then the performance of our filter is evaluated against through simulation using PSIM software against the well filter 3-wire topology and a 4-wire topology presented in 4 on PSIM software. Then finally, we also develop or implement practically 2 filters. The first one is filter topology, a filter designed based on the topology we have introduced in this paper, and the other is designed based on the methodology outlined in paper 2 in this paper. And then practical comparison of the common mode current was conducted among the 3 systems. That means among the proposed topology, well filtered 3-wire topology, and the topology suggested in 2 at a various motor speed. So the result is as follows. So as you can see, this is common mode current measured, the actual common mode current measured at 0 revolution per minute at standstill. So as you can see from the simulation result, compared with the well filtered 3-wire topology and the 4-wire topology, the proposed one shows a reduced common mode current than the others, and the same is true for the motor at a speed of 475 revolution per minute, and when the motor is at 954 revolution per minute. So overall, both the simulation and the experimental result indicate that the proposed neutral filter topology exhibits lower common mode current compared to the well filtered 3-wire top system, and a neutral filter exists in the literature for the frequency range of interest. Moreover, the proposed filter is designed with a limited neutral current, less percentage of overshoot, and less power loss on the neutral wire. Okay, the third paper is it's a review paper. It is on overview of shaft voltage and bearing current mitigation method applied at the victim machine. This is also a complete paper. It is a review paper which was authored by me and my Ethiopian professor. This paper is already accepted for publication at the Springer Journal of Electrical Engineering. So I will not talk much about this paper, but to say a few words, it is known that mitigation of shaft voltage and bearing current is well known in the literature. There are so many mitigation methods to mitigate the shaft voltage and bearing current. For instance, the bearing, the insulated bearings, the ceramic bearings, the shaft grounding methods, like the Faraday's shielding method, the conducted grease. These are the most common and very well known mitigation strategies that are applied to mitigate the shaft voltage and bearing current approach. But in this paper, we want to focus on the recent mitigation methods that has been published recently in the paper, in the literatures. This is the geometric modification method. So these days, apart from the already existing saturated research, now people are using the geometric modification methods. That means by modifying the motor geometry, it is also possible to mitigate the shaft voltage and bearing current. For instance, by adjusting the winding design, by altering the machine stator and the rotor geometry, insulating the rotor surface, and by modifying the stator slot wedge, we can mitigate the shaft voltage and bearing currents. So the key advantage of this is this approach is it doesn't require any additional materials that could lead to increase the size, weight, and the cost of the machine. So saying this, let's say something about my teaching experience. I've been working since from 2008. For 2 years I've been working as a graduate assistant, so in charge of giving tutorial class and assisting the laboratory classes. From 2012 to 2019 I was been in charge of delivering lectures and evaluating undergraduate students. Some of the courses I've taught are the Introduction to Electrical Power System, Introduction to Electrical Machine, Fundamental of Electrical Engineering, the Basic Electrical Engineering course, and the Power System Analysis. I've also been served as Associate Dean for Academic and Student Affairs for about 2 years. And finally, let me say something about my technical experience. Throughout my career, I've been experienced in some computer applications, like I can use LaTeX, LibreOffice. I can use Microsoft Visio for drawing the circuits, and I can use, and I've been used MATLAB. I've experienced it with Simulink as well, the command window, and then I've also experienced it with COMSOL multiphysics, especially the finite element analysis model of the machine. I have also experienced it with PSIM simulation, power electronic simulation, LT Spice, Code Composer. Actually, I can run the Code Composer, but I've not such experience on this area, but I can use that already designed Code Composer, but I cannot design by myself. And regarding to laboratory measurement equipment, I'm able to use impedance analyzer to measure the common mode differential mode impedance or impedance of the machine. I can use the LCR bridge, oscilloscope, current probe, tachometer, and some other laboratory measurement devices, and I have the ability to design and implement inductor. I can design my inductor by myself. I will not buy it. I can design the motor stator coil, especially for induction motor. If the coil is failed, I can rewind it. Especially I used to do this with my undergraduate student. I can design and implement common mode choke, contactor coils, filters. I can implement my circuit on PCB, print circuit board. I can design and implement domestic and industrial electrical installation and controls and much more. And finally, I can say thank you so much for listening to me with the great patience. Thank you so much. And I can say finally, I'm ready and committed to learn from you and serve the best of my knowledge and ability for you. Thank you very much indeed.